Fusion sees this sheet metal part as just a solid. Let's convert it into a Fusion sheet metal part, generate the flat pattern, and export a clean DXF, ready for manufacturing. Here's the step file I'll be working with. I'll rotate it briefly so we can take a look at the overall geometry. Before making any changes, I'll save it as a Fusion design. This gives us a proper working copy, so the sheet metal conversion and the features we create from here are stored with the design. Next, I'll use the Measure tool from the Inspect panel. It's a quick way to check existing dimensions directly from the model. First, I'll measure the sheet thickness. Here it's exactly 2 millimeters. We'll use this value when we create our sheet metal rule. Now I'll measure the inside bend radius as well, which is 3 millimeters. This will become the bend radius in our rule. These geometric values should match the imported part, but keep in mind that an accurate flat pattern also depends on manufacturing data, such as the K factor. That value should ultimately come from the actual material, tooling, and bending process. Now I'll switch to the sheet metal workspace, where we have the tools specifically designed for sheet metal parts. Before converting this imported solid, we need to define the sheet metal rule that Fusion will use to calculate the bends and ultimately the flat pattern. I'll open the sheet metal rules library from the Modify panel. Fusion already includes a number of predefined rules, so instead of creating everything from scratch, I'll copy one of them and modify it for this part. The copied rule is added to the Shared Rules folder. I'll open it for editing and first give it a unique name, just to avoid confusing it with the original rule later. For this example, there are 3 parameters we really need to pay attention to: thickness, bend radius, and K factor. Thickness defines the actual sheet thickness. We already measured our part at 2 millimeters, and this rule is already set to 2 millimeters, so I can leave it unchanged. Next is the bend radius. This needs to match the geometry of our imported part, so I'll update it to the 3 millimeters we measured earlier. And finally, the K factor. This controls the position of the neutral axis through the bend and directly affects the developed length of the flat pattern. For this demonstration, I'm using a K factor of 0.44, which is already entered here, so I'll leave it as it is. I'll also change the 3 bend corner relief radius to 3 millimeters. Our current part doesn't actually have a corner where 3 bends meet, so this setting won't affect this model. I'm changing it here simply to show where you would control the relief if your part did contain that type of corner. Now I'll click Continue and review the changes before saving the rule. Everything looks correct, so I'll save it. Fusion gives us one final summary of the values in the rule, and we can quickly confirm that everything is set correctly. Our custom sheet metal rule is now ready. With our sheet metal rule ready, I'll go to the Create panel and choose Convert to Sheet Metal. This command lets us convert a uniform thickness solid body into a proper Fusion sheet metal component. For the source face, I'll select the main flat face at the base of the part. Fusion automatically recognizes the sheet thickness from the existing geometry. Now I need to assign the sheet metal rule we created earlier. Once I select it, I can confirm that the units, thickness, and K factor are all using the values we defined. Everything looks correct, so I'll click OK to complete the conversion. And there's an important visual change here. Before the conversion, the icon in the browser was a simple cube, indicating a standard solid body. After converting it, that icon changes to the sheet metal icon. We can also see the assigned sheet metal rule in the browser. So Fusion is no longer treating this as just an imported solid. It now recognizes it as a sheet metal part, which means we can start using sheet metal specific features such as unfolding and creating a flat pattern. Now I'll go to the Modify panel and choose Unfold. Since Fusion now recognizes this as a sheet metal part, the model is ready to be unfolded. The Unfold command first asks us to select a stationary face. I'll use this large flat face at the base of the part. Fusion then identifies the bends connected to this face and unfolds the model using the sheet metal rule we assigned earlier. I'll click OK to complete the operation. Now we can inspect the unfolded geometry from a few different angles. And using the timeline, I can move before and after the unfold feature to compare the folded and unfolded states of the same part. One important point here: unfold is mainly a temporary modeling state. It's useful when you need to work on the part while it's flattened, but it is not the same thing as the production flat pattern we'll create later. Next, I'll go back to the Create panel and choose Create Flat Pattern. Right now, the part is still in an unfolded modeling state, so Fusion asks me to refold it first. That's an important distinction. Unfold is a temporary modeling operation, while a flat pattern is a separate manufacturing representation generated from the folded sheet metal part. I'll refold the model and run Create Flat Pattern again. Fusion asks for a stationary face, so I'll select the large flat face at the base of the part and click OK. The flat pattern now opens in its own environment. Notice the bend center lines and extent lines around the bend regions. These are useful manufacturing references, and we can control their visibility directly from the browser. I'll toggle them on and off here so you can see exactly what they represent. Now I'll click Finish Flat Pattern to return to the folded model. And if you look at the browser, Fusion has created a separate flat pattern node for this component. This is important because the flat pattern is now stored with the sheet metal part. At any time, I can right-click it, choose Activate, and return directly to the flat representation. That's exactly what I'll do now. With the flat pattern active, I'll choose Export. For this workflow, I'm exporting the profile as a DXF, which is a common format for laser cutting and other 2D manufacturing processes. I'll keep the units set to millimeters. Next, I'll enable Convert Splines to Polylines. Some downstream cam and cutting software handles polylines more reliably than spline geometry, so this can improve compatibility. The tolerance controls how closely the converted geometry follows the original spline, and for this example, I'll leave it at the default value. Under Visible Geometry, I'll turn off center lines and extent lines. Those lines are useful as bend references, but for this export, I want a clean-cut profile without additional bend geometry that could be interpreted as cutting paths by downstream software. Everything looks correct, so I'll click OK and export the DXF. At this point, our DXF is almost ready to send for cutting. Before saving it, I'll take a closer look at the exported geometry and perform one quick dimensional check. Using the Measure tool, I'll check one of the mounting holes. The diameter is exactly 6 millimeters, which matches the original model. This is a simple but useful verification step. Before sending a DXF to manufacturing, it's always a good idea to confirm at least one known dimension to make sure the geometry and scale were exported correctly. Everything looks good, so I'll give the file a clear name and save the DXF. Now we have a clean, dimensionally verified cut profile ready for manufacturing. And that's it. We started with a simple imported solid and ended with a proper Fusion sheet metal part, a flat pattern, and a clean DXF ready for manufacturing. If you found this useful, subscribe for more practical CAD and engineering workflows.